Hello, this is mathjazz from Almost Cool, and I have a video on basic set theory definitions aimed at my finite mathematics class. So, here are basic set theory definitions for the purpose of finite math. First, a set is a collection of objects, and the important part about a set is that you're able to tell whether or not an object is in the set or not. There are several ways to define a set. We do it all the time in English using just regular words. When we talk about the books on my bookshelf, the people that live in Siberia, the number of the set of even numbers. We talk about sets all the time in normal conversational English. And so that's a perfectly valid way to define a set. It tends to become cumbersome in mathematical papers because writing the same clause or phrase over and over again takes a lot of space on the paper. So we can also, we usually get some shorthand in our sets and we name them. So we can define a set with words, we can list the objects of the set explicitly, like this set here, pig, cow, duck, dog, cat. And once we've defined what the objects are, then we usually give it a name, usually a one-letter capital letter name, and we refer to the set by that letter for the remainder of the time we're doing work, the time that we're doing writing our paper, doing our research. Another way of defining an object, defining a set, is to use set builder notation. So set builder notation, it has these curly braces that we use when we explicitly list the objects of a set, but it also has a vertical line in it. On the left side of the vertical line, we write what a generic object will look like in the set, and on the right side, we'll write restrictions to the generic object that will define the set. For example, this is a set that's written in set builder notation, and it's probably just as fast to write 1, 2, 3, 4, and 5 than to write this, but this is an easy set to grasp and understand, and it has the properties that we're looking for. That is, here are curly braces, here's our vertical line. To the left of it, we say objects look like whatever this variable is going to mean. And on the right side, we put restrictions on this variable. So for example, x is our generic element, and the restrictions we place on it are x is a natural number, and x is less than or equal to 5. So this set here is the set 1, 2, 3, 4, 5. But we need to feel very comfortable with set builder notation to succeed in the class, and we will see lots of problems that will give us familiarity with this. Some other definitions we need. We need to define what an element is. So an element of a set is an object that is in the set. If an element is in the set, we write it as x, the symbol that looks kind of like an E, and then the name of the set, in this case A. So x is an element of the set A is written x in A, or this E symbol means in, or is an element of, is another way of interpreting that symbol. If x is not an element of A, we write x and then the same in symbol, but with a slash through the symbol, and then the name of the set. So x is in A and x is not in A, are how we read those terms, those expressions. Okay, so now we talk about subsets and containment. So suppose that we have two sets, A and B. A is a subset of B if every element of A is also an element of B. For example, the even numbers are a subset of the natural numbers, or the integers. Every even number happens to also be an integer. So therefore, the natural numbers are a subset of, the even numbers are a subset of the integers. Another way of wording that is going to be that B contains A, or A is contained by B. We write this as A with this sideways U symbol, and then B. So A is the set that is small and inside of the other set. B is the set that is bigger and contains the first set. The U shape opens toward the bigger of the two sets, the one that contains the other. Okay, so also less commonly we call B a superset of A. That's not a very common term, but it does come up from time to time. So if every element of A is an element of B, then A is a subset of B. B contains A is contained by B, and B is a superset of A, are all ways of saying the same thing, and this is the notation. A, this sideways U shape, and then B. Set equality. So we know what equals means in terms of numbers. We know that 4 is equal to 2 plus 2, but we also have an idea of what equality means between sets. So suppose that A and B are sets. If every element of B is also an element, if every element of A is also an element of B, and every element of B is also an element of A, then A and B are considered equal as sets. We write that with the usual equal sign that we use for numbers, where we just write them between two sets and say the sets are equal. And we note that it is exactly the same to say A equals B as to say that A is contained by B and B is contained by A. So if you have two sets and they each contain the other, they're equal. And vice versa. If two sets are equal, then they each contain each other. It's usually easier to prove sets are equal by proving one contains the other and then proving the other contains the first. If you're writing out a proof, it's usually easier to prove one-way containments and then say, hey, look, I have both one-way containments, therefore I have equality, than it is to prove equality right off the bat. Okay, so the next term we need is union. So we start off with two sets. The set that contains exactly the elements of A and the elements of B is called the union of A and B. That is, everything that's in the union has to be in A or B, or both, and everything that's in A or B or both is in the union. So this is how it's written. A union B is how this is read, and it's A with a little U symbol and then B. Intersection is the next term that we need. So suppose that A and B are sets. The set that contains exactly the objects that are elements of both A and B is called the intersection of A and B. Now, this sounds very similar, but the intersection is all of the stuff that is in both A and B. That is, every element of the intersection is in A and it's in B. Whereas with our union, every element is in A or it's in B, or it's in both. And in mathematical language, we usually mean or to mean, instead in regular conversational English, when we say this or that, we mean exactly one of those, either the this or the that, but not both. In mathematics, we usually say or to mean this or that or both. It's automatically assumed when you say A or B that both of them might be happening at the same time. It's not an exclusive or is the term for what we usually mean in English. In English, exclusive or means one or the other and not both. And in math, the usual or is inclusive. It's one or the other or both. So that is something that students do get hung up on, and this is just purely by convention. mathematicians decided that it is important for all of us to know exactly what we mean, and this is the decision that was made. So, getting back to intersections, the intersection is denoted A intersect B with this upside down U shape. I like to think that the upside down U shape looks like an A with the missing bar in the middle, and that missing bar A means and. So A intersect B means the stuff that's in A and in B. And that upside down U shape, which looks kind of like an A, is for the and. It's all the stuff that's in A and it's in B. Okay. So now we talk about set subtraction. So set unioning is kind of like set addition almost. Set intersection is not really similar to either addition or subtraction or any other regular number operation, but set subtraction is similar to the subtraction of numbers in that the set contains exactly the objects that are elements of A, but not elements of B. You think of it as you take all the elements of A, and then you go through and delete the ones that are in B. You subtract out the ones that are in B. And what you're left with is called the set difference between A and B. We write it like so. So A minus B goes A, and then the slash, and then B. So we take all the elements of A, we delete the ones that are in B. Notice that for unions and intersections, the order does not matter. A union B is the same as B union A. A intersect B is the same as B intersect A. But it is not usually the case that A minus B equals B minus A. And that's actually kind of a lot like subtraction. With multiplication and addition, doesn't matter if we're doing 1 plus 2 or 2 plus 1, it's the same. Doesn't matter if it's 3 times 5 or 5 times 3, it's the same. But 3 minus 5 is different from 5 minus 3. And that is the case in sets as well. It is rare to have a set A minus a set B equaling a set B minus a set A. The next term we need is universe. So a universe is a collection of objects that contain sets. That is, the universe contains objects, but it also contains sets. The objects are elements of the universe. The sets are subsets of the universe. So now we can define complement because that's impossible before we define universe. Suppose A is a set in a universe U. The complement of A is the set of objects in U that are not in A. The letters are backwards. Those will be fixed on the slides. But yeah, so the complement is the set of objects that are in U that are not in A. And it's denoted A prime. And if we change the universe, then we change the complement. So that's what we mean by the complement of a set depends on the universe that it lives in. We define proper subset. So first we set up a set with its subset. So B is a set, A is its subset. A is a proper subset of B if there are elements of B that are not in A. So, for example, the even numbers are a proper subset of the integers because there are integers that are not even. Whereas the even numbers are not a proper subset of the numbers divisible by 2 because there are no numbers that are divisible by 2 that are not even. Okay, so most subsets of a set are proper. The only subset that's not is itself. So every set is a subset of itself because, of course, all of the elements in a set are in the set. And therefore, every set is a subset of itself. But every set is called the improper subset of itself. So if you have a set that you have subsets inside of it, it itself is called the improper subset. And all of the other subsets are called proper subsets. Another important set is the empty set. A set with no elements in it is called the empty set. So it's most commonly denoted as the symbol that looks like a zero with a line through it, but it's also sometimes written as two braces with nothing between them. So we notice that since the empty set has no objects in it, every object of the empty set is in every other set and in every universe. So the empty set is a subset of every set, and it's a set in every universe. So one other thing is, as long as we're talking about proper sets, if you have a set B, B is an improper subset of itself, and the empty set is called the trivial subset of itself. So every set has at least two subsets. They're itself and the empty set, or the improper set or the improper subset and the trivial subset. Except for, of course, the empty set, which the trivial subset of the empty set is also the improper subset of the empty set, and it's a little strange to think of it. But okay, so to end the video, we're going to claim that all set operations, that is union, complement, intersection, set, subtraction, can be written in terms of set builder notation, and we define them this way. This is how most mathematicians think of unions, intersections, differences, and the like. This is more, it's shorter to write this than it is to write out the definitions in English. And so this is kind of how most mathematicians would think about the definitions. I mean, they might think about it in words, but this is the clean, short way that they would write them. And I leave that as an exercise to you, the viewer, to figure out why each of these left-hand sides of the equal signs are equal to the right-hand sides. And the way you do that is you show that every element in the left is on the right, every element on the right is on the left. We'll probably have a video up showing the proofs of these at some point, but think about it yourselves. And thank you for watching the video. Hope you're having a great day, and have a great day. Bye.